Now let's prove this theorem. Proof. We have here two cases. First of all, we will prove the part about the local asymptotic stability and then instability. But we will have two cases in that part and two cases in this part also. First of all, we show that this condition holds if and only if the eigenvalues of J is have the magnitude less than 1. This is part 1. Okay, let's write that. Part 1. Trace J is less than 1 plus determinant J, and it is less than 2 if and only if all eigenvalues have the magnitude less than 1. And because here we have if and only if, we have two sides. We want to show that, sorry for this, if this happens then this will, if this happens then this will. Okay, so because of that, I will start with this way first of all, and then I will show that way. But before this, let's make the notations easier, because I don't want to write trace J and determinant J usually too many times here. Now denote tau as trace J and delta as determinant J. First of all, then the characteristic equation will be P of lambda, which is lambda squared minus tau lambda plus delta equals 0. This is the characteristic equation. And the eigenvalues are roots of P lambda lambda 1 equals tau plus square root of tau squared minus 4abec over 2. Lambda 2 is tau minus square root of tau squared minus 4 delta over 2. Okay. We want to show that this statement holds. And to do this, first of all, I will start with this way. Case 1 in part 1. So I want to show that this side, which means suppose first of all, we can write this here. Okay, suppose lambda I is less than 1, and they can be real or complex, and first of all I want to assume that they are real, and eigenvalues are real. Okay, now let's look at the formulas. If they are real, first of all we know that tau squared minus 4 delta is greater than or equal to 0. Okay, we know this first of all. On the other hand, if we analyze the P lambda here, this is a parabola, and because the coefficient of lambda squared is 1 and it is positive, arms open upwards. On the other hand, vertex of this parabola can be calculated minus b over 2a and f p of minus b over 2a formula. B is minus tau and a is 1. So I have tau over 2 p tau. If I substitute tau over 2 here, then I will obtain tau squared over 4 minus tau squared over 2 plus delta, which is minus tau squared plus delta over 4. And because this is positive, this will be negative. Because of that. Okay. So the graph of this parabola will be something like that. This is vertex, occurs at tau over 2. And this is p tau over 2. And they are roots of p lambda, which are lambda 1 and lambda 2. And from here you can directly see that lambda 2 is less than lambda 1. So this is lambda 2, this is lambda 1. Okay. And I can write that lambda 2 is less than or equal to tau over 2 and it is less than or equal to lambda 1. As you can see, this is a real line. We have lambda here, p lambda here. Okay. So I will continue from there. Since absolute value of lambda I is less than 1, we have minus 1 is less than 1, lambda 1 and it is less than 1, and minus 1 is less than lambda 2 and it is less than 1. They are real, so because of that we can open it like that. And on the other hand, we know this, plus I know that lambda 2 is less than or equal to tau 2 over 2 and it is less than or equal to lambda 1. So as a result, we have the following. Minus 1 is less than lambda 2 and it is less than or equal to tau over 2. And it is less than lambda 1 and lambda 1 is less than 1. So as a result, tau over 2 is between minus 1 and 1. So I can say that the absolute value of tau over 2 is less than 1, which means absolute value of tau is less than 2. Okay, we have these and we will use it. If tau is absolutely less than 4, can I say this? Tau squared is less than 4? Yes. On the other hand, from here, I know that this is one side. Tau squared is greater than or equal to 4 delta from here. So I know this. Plus this, tau squared is greater than or equal to 4 delta, which means 4 is greater than tau squared and it is greater than or equal to 4 delta. So I will write the following directly. Let's take this and we will use it. Now, I have another analysis here. I know this, right? We have such a real line. This is tau over 2, lambda 1 and 1. So if you look at this, you can directly say that this difference is greater than that difference. So I have absolute value of tau 2 over 2 minus 1 is greater than tau over 2 minus lambda 1. On the other hand, I have this. Here we have minus 1. Here we have 0, lambda 2, and tau over 2 from here. I know this from the graph. Okay. So, for this time, this difference is greater than that difference. So I have tau over 2 minus 1 greater than, let's write only greater than, tau over 2 minus lambda 2. Because we know that lambda 2 is different minus 1 and lambda 1 is different 1. And so because of that, I erase the equalities here. And this part is tau over 2 plus 1. Now I want to analyze these sides. Okay. Plus tau over 2 minus lambda I. What should be? I have tau over 2 minus lambda I is the following. Tau over 2 minus plus square root of tau squared minus 4 delta over 2 in the absolute value, and this will be a cancel, right? So I have minus plus square root of tau squared minus 4 delta over 2 in absolute value. This is positive, so the result is square root of tau squared minus 4 delta over 2. Okay. So we have the following. If I replace lambda 1, lambda I by lambda 1 and lambda 2, I have the same result. So I will write this like that. In the absolute value, tau over 2 minus 1 from here greater than this, which equals this one. And from here I have tau over 2 plus 1 is greater than same thing. Okay. Now, this is equal to, if you look at this side, this distance is 1 minus tau over 2. And this distance is, here this one is 1 plus tau over 2. So, this and this can be represented using the following notation. I have 1 minus, in the absolute value of tau over 2 is greater than only square root of tau squared minus 4 delta over 2. Okay. If tau is negative, I have 1 minus tau over 2. If tau is positive, I have 1 plus tau over 2 here. Now I want to take the square of each side. So what we have here, square of this side is 1 minus 2 times this term, which is absolute value of tau, and plus square of this side is tau squared over 4 greater than tau squared over 4 minus delta. I can cancel these, which means I I just take this to this side and this to this side. 1 plus delta is greater than absolute value of tau. So result will be this. If lambda I is less than 1, then it implies that tau in the absolute value is less than 1 plus delta, and where is the term here? And from here we know that 4 is greater than 4 delta, which means 1 is greater than delta, so 2 is greater than 1 plus delta. So I will write it here, less than 2. So we have shown that the one side of this statement. Okay. Now it's time to show the other side. Sorry, not the other side. First of all, we should show the second case here, case 2 in that side. Which means, again, we assume that here, suppose lambda I is less than 1 and eigenvalues are complex. Which means the term in the square root is less than 0. Okay, for this time we will continue with this. And now the eigenvalues can be rewritten like that. And if you use the I notation, this is the real part and this is the imaginary part. And let's check the magnitude here, okay? The magnitude of those eigenvalues will be square of the real part plus square of the imaginary part in the square root, of course. So we have in the square root tau squared over 2, not 2, 4, plus square of this side is 4 delta over 4 minus tau squared over 4, which is equal to square root of delta. And we know that from here, from this, here, a square root of delta is less than 1, which means 0 is less than square root of delta is less than 1, so 0 is less than delta, delta is less than 1. Okay, we have this first of all. On the other hand, if you look at that one, this is one thing. And if you look at this, for this time you will see that tau squared minus 4 delta is less than 0, which means tau squared is less than 4 delta, which means tau is the absolute value of tau is less than 2 square root of delta, okay? And this is less than 2 here, okay? And we know that square root of delta is less than 1. But we need 1 plus delta here. So how can I write this? This is 1 plus delta. I can obtain this inequality with that. We know that 1 plus square root of delta square is 1 minus 2 square root of delta plus delta, and this is greater than 0. So I just take to this side 1 plus delta is greater than 2 square root of delta. okay? And I know that delta is less than 1, so this is less than 2. As a result, I can show the same thing now again. If you have a complex eigenvalues, still you have the same thing. Okay. Now let's talk about the second way. I mean this way. Now we assume that tau is absolutely less than 1 plus delta, and it is less than 2. And we want to show that the magnitudes of eigenvalues are less than 1 here. So we have case 1, first of all. Now we assume that this happens and eigenvalues are real. So, first of all, we know this from the graph. This is lambda 2, and this is 0, and this is tau over 2, this is lambda 1. And because they are real, we know that tau squared minus 4 delta is greater than or equal to 0. We know this first of all. So from here, I can say that lambda 2 is less than or equal to lambda 1. Okay. Now we want to show that it will be enough actually. It is enough show that because we want to make them between minus 1 and 1. Minus 1 is less than lambda 2 and lambda 1 is less than 1. Now let's first of all start with magnitude of tau, absolute value of tau less than 1 plus delta. If we rearrange this, we will have minus delta is less than 1 minus absolute value of tau. And now I will add the tau squared over 4 to each side. So we have the following. This part is greater than or equal to 0 because of that. Okay, 0 is less than or equal to tau squared over 4 delta over 4. And this is less than, if you look at this, this is the open version of this full square. Okay, so this full square is greater than 0. And now if I take the square root of each side, I will have the following. Because this is positive, I can leave it like that. And this is also positive. So we have 1 minus absolute value of tau over 2. Now it will be enough to take to this side because lambda 1 is the sum of that and this. We know that. Okay. We have obtained this. On the other hand, lambda 1 is tau over 2 plus this part. If tau is positive, they are equal. So lambda 1 is less than 1. If tau is negative, then this will be greater than that one. So since this part is this sum is greater than or equal to lambda 1, we have as a result lambda 1 is less than 1. So this is done. Now it's time to show the other side. For this time, I want to use the following. I will, from here, I will continue like that from here. Until this step, everything is same. But after this step, I will just take the following like that. Minus 1 is less than, take this to this side, this to this side, minus absolute value of tau over 2 minus square root of tau squared minus 4 delta over 2. And again, lambda 2 is minus tau over 2 plus square root of tau squared, sorry, not minus, plus minus tau squared minus 4 delta over 2. So this is less than or equal to lambda 2 here, this part. As a result, minus 1 is less than lambda 2. So this is also done, which means minus 1 is less than lambda 2 is less than or equal to lambda 1, it is less than 1. So the absolute value of lambda I is less than 1. So this part is also done. But this is not enough because we may have complex eigenvalues also. I have case 2. Again, we assume that absolute value of tau is less than 1 plus delta and it is less than 2. And eigenvalues are complex. And we have calculated it before. The magnitude of lambda i's if the eigenvalues are complex. Here we calculate it. The magnitude equals square root of delta. And magnitude squared will be delta. Okay. So from here, if you check that one, you can see that delta is less than 1, so I have less than 1. So directly, if the square of something is less than 1, this thing is also less than 1. We have shoved this, it directly. Now I can move on to part 2. Instability, being instability. First of all, let's summarize this. Now we know that lambda I is less than 1 if and only if absolute value of tau is less than 1 plus delta and it is less than 2. What is the meaning of this? Meaning of this is that these parts have the same meanings. First of all, if you check this, first of all, this inequality, I have minus 1 minus delta less than tau. Tau is less than 1 plus delta. So from here we have tau is less than 1 plus delta, or tau is greater than, or you can write it like that. Tau is greater than minus 1 minus delta. From here we have delta is less than 1. So if one of them does not hold, okay, not or actually this is and, and this is also and. If one of them does not hold here, then at least one of the eigenvalues have the magnitude greater than 1. So because of that, we can conclude the following results. From here, if tau is greater than 1 plus delta, or if tau is less than 1 minus delta, or if delta is greater than 1, we will have this side does not hold results. So it means the magnitude of lambda I will be greater than 1. Okay, so it means equilibrium solution is unstable. Now, as you can see, if you have less than, we have localized totally stable result. If we have greater than or this part, then we have instability result. So, if we have equalities, we have the boundaries of the stability region. Let's sketch the stability region. Boundaries tau equals 1 plus delta, or delta equals tau minus 1, tau equals minus 1 minus delta, or delta equals minus 1 minus tau, and delta equals 1. Why? If delta is less than 1 and this is greater than this, or this is less than this, we have stability. If one of them does not hold, we have instability. So because of that, the region will be this. Okay, so I have tau versus delta. Coordinate system. This is 1, this is 1, this is 2, this is minus 2. I have 1 here also, minus 1 here also. These are lines, right? This is a line. And it passed through 0, minus 1, and 1, 0, 0, minus 1, and 1, 0. So this is a line something like that. Okay, also when x is 2, tau is 2, the value is 1 here. Okay. And that one is 0 minus 1 again. And if tau is minus 1, for this time delta is 0. So it passes through from here to something like that. Again, it takes the value 1 when tau is minus 1, minus 2. Okay. And this is delta equals 1. So if you are inside this triangle, the equilibrium solution is local asymptotically stable. If you cross these boundaries at least one of them from inside to outside, then you will obtain an unstable equilibrium solution. Also, we can determine the real or complex eigenvalues by the sign of tau squared minus 4 delta is sign of this function. So if I equate it to 0, I have delta equals tau squared over 4 parabola. It is something like that. The vertex is 0, 0, and the only root is 0, 0. When it tau is 2, value of delta is 1, and at minus 2 also we have same value. So when this is positive, for example, if you substitute 1, 0, 1 here, you will obtain negative number. If the points are below this curve, you have real eigenvalues. If they are above this curve, then you have complex eigenvalues. Okay, I want to write a note here. When one of the inequalities in the local stability criteria if one of them does not hold, at least one eigenvalue either lies on the unit circle in the complex plane, which means the magnitude is greater than 1, or outside of this unit circle, or outside of this unit circle. Okay. Which means the magnitude is greater than or equal to 1. And we can summarize it like that. If the trace j is greater than 1 plus determinant j, tau is greater than 1 plus delta here. Below that line, then eigenvalues are real, but magnitude is greater than 1. Lambda 1, sorry. Lambda 1 is greater than 1. If the trace j is less than minus 1 minus determinant j, here, if it is here, then for this time, again eigenvalues are real, but lambda 2 is less than minus 1. If the eigenvalues are complex and delta is greater than 1, if you are here, then magnitudes are greater than 1. Okay, this is the first note, and I have one more note, and then we will have an example. The region of the local asymptotic stability is graphed here, crossing one of the three boundaries, one of these three boundaries from inside to outside of the parameter region. We will have a positive eigenvalue which is greater than 1, or negative eigenvalue less than 1, or complex pair satisfying. Actually, we just said the same thing like that. across the 3, one of the 3 boundaries of the region of local asymptotic stability from inside to outside results then either a positive eigenvalue we have greater than 1. This happens in the boundary tau equals 1 plus delta, okay? Or a negative eigenvalue less than 1, minus 1, and this happens on the boundary tau is minus 1 minus delta, or a complex pair satisfying lambda I greater than 1, and this happens on the boundary delta equals 1. Okay.